Hello, welcome to our third video in the Gen Chem series. And today we're going to be talking about periodic trends. So I'm actually really excited about this video because it is a super, I kind of almost think of it as a ultra high yield MCAT topic. So this is really one of those things that seems to appear pretty much on every exam, at least in one question. More so than that, I think it's ultra high yield because this is a incredibly foundational topic. It's one of those things that really helps explain a lot of other things. For example, one of the other topics that comes up a lot on the MCAT is intermolecular forces and like hydrogen bonding, bond polarity, that sort of thing. Um, And that really actually all boils down to the periodic trend. It really does. It's kind of crazy. But the periodic trends basically explain away most of intermolecular forces. So I want us to feel really good about this as a concept. I think it's something that a lot of people just kind of memorize, especially when they maybe first learn it for Gen Chem and are cramming for exams. I really want you to kind of like physically understand what's going on with it and really understand it, because trust me, it's going to pay off a lot as we kind of move into harder topics. Okay, so all that being said, um, I want to kind of begin with really the origin of all trends, which is effective nuclear charge. So, effective nuclear charge, I would actually say, is basically all the other periodic trends are effective nuclear charge, just in disguise. So, I want to spend extra time on this one, and let's kind of break down what it is. So, nuclear. Let's break down the words. Nuclear means like nucleus, obviously, or maybe in this case, protons. And effective, I'm going to break down to meaning like how much. So, really, effective nuclear charge is how much of the nucleus or the protons the electrons feel. So, that's what it is. It's how much of the protons um, do the electrons feel. And so, what do I mean by that? Let's kind of get into the nitty gritty. So, um, if we're looking at a inner shell electron, oh, by the way, what atom is this? Hopefully, you've kind of figured that out. It's got four protons. So if you've got your periodic table, you would see that this is beryllium. This would be beryllium. Okay, so the inner shell electrons, let's see kind of how much proton force that they feel, right? So if you're an inner shell electron, that means you're going to feel like the pull, the force of these four protons, right? So I'm going to draw kind of four arrows showing that. And that would be the inner shell electron's effective nuclear charge. And then let's also consider the valence electron. So things are going to get a little different for the valence. Yeah, so the inner shell is four. So the outer shell or the valence electrons, they also are going to feel the kind of proton force of four, right? They're going to have four arrows going in, and maybe like the magnitude or the size of these arrows might be like a little smaller than the inner shell electrons because they're further away, right? So the force kind of falls with distance. Mm. But they still feel those four protons, right? So you might think, okay, it's basically four, maybe a little bit less than four. But there's another thing we need to consider here. And that other thing is the fact that the electrons themselves are charged, right? So if we kind of consider what's happening with the inner shell electrons to the outer shell, those inner shell electrons are going to repel the outer shell electrons. They're going to push them away, right? So they're saying, actually, like, move away, get out of here. Like they're pushing them away with their repulsive force. And so what's going to happen is effectively those four protons in the nucleus are going to cancel out with the two inner shell electrons. and that's going to equal an effective nuclear charge of 2, right? Okay. And just in case you were wondering, you might be wondering two more things. Well, what about the inner shell's electrons? Aren't they being repelled to the valence shell? And yeah, they are. They're also going to be repelled for sure. But consider the fact that the arrows are going to be pushing into the nucleus in that case. So if I were to draw those arrows, they would actually be helping kind of the effective nuclear charge. They would be pushing those inner shell electrons even closer. Um, and then we might be wondering about the repulsive force of the other valence electron, right? So what about the repulsive force of that valence electron, the second valence electron? And that we're going to basically consider to be negligible, because remember, if these were more accurately drawn in their orbitals, they would be kind of occupying lots of different space. And for much of that space, um, one of them will be closer to the nucleus than the other, but then the other half the time, they'll kind of reverse in places. So it kind of ends up canceling out into zero. So maybe that's not the best explanation, but just kind of trust that when we're doing effective nuclear charge, we're really only considering the inner shell electrons effect on the valence shell electrons. Okay, that being said, let's get a bit more practice with this and see the trend part of this periodic trend. So I've drawn 4 atoms here. Let's go ahead and identify them and calculate their Z effectives, their effective nuclear charges. So I would recommend pausing the video for a quick second because I'm going to do this pretty quickly. All right, so the first atom is going to be um, lithium, and then we've got beryllium, and then boron, and finally below lithium, we've got sodium. Okay, so to calculate the effective nuclear charge, you would always kind of do this from the valence electron's perspective. So the valence electron for lithium feels 3 protons, um, but has 2 inner shell electrons canceling. So it would be 3 minus 2, and it's going to equal 1. Beryllium we already did, and that was 2. And boron, kind of following the same logic, is going to be 3. Then if we did sodium, don't be intimidated by the fact now that we have 3 shells. If you're looking from the valence electron's perspective, everything closer, like in the shells closer than it, we're going to count as like kind of blocking a proton. So since it has 11 protons and there's 10 electrons blocking, that means that this valence electron has a Z effective of 1. Okay, so now we can kind of see the trend, right? So if we were to kind of generalize this, we can see that as we move to the right on the periodic table, our Z effective gets larger. And as we move down, it appears to be the same. That might feel a little off to you though, maybe because you remember from Gen Chem that the trend actually decreases as you move down a column, or maybe that seems off for other reasons. So I want to challenge you for a quick second to think about why, even though it seems like the effective nuclear charge of lithium and sodium are the exact same, why does it actually decrease as you move down that column? So sodium's is actually going to be a little lower than lithium's. Okay, and the main reason for that is just simply the distance, right? So this, we can actually be precise about where the electrons are. Um, This lithium electron, its valence, is going to be in the 2s orbital, and the sodium's is going to be in the 3s, which means that the sodium's valence electron is just simply further away. It's quite a bit further away because it's in a higher energy orbital. And if it's further away, that means it feels less of a pull from each one of those protons. So even though it's kind of the same like math, where like there's the same effective nuclear charge using our little formula, it ends up being that it's a little bit less in the case of sodium because that electron's further away. All right. So let's just quickly generalize what we've figured out. So effective nuclear charge seems to increase as we go from left to right and increase as we go from the bottom to the top of the periodic table. Um, the next trend that I want to look at is atomic radius. Atomic radius, which in my brain, I just kind of instantly translate this to size. I don't know. It just makes more sense to me, and I'm probably just going to call it size for the rest of the video. So let's think about how the trend of size works. I think this one is probably like generally the most confusing and like the most surprising, I think, for a lot of students. Um, but now that we feel, hopefully, are feeling really good about effective nuclear charge, I'm really hoping it's going to make sense why it's kind of surprising. So right away, let's just address kind of the easier bit, which is if we're looking down a column, right? If we're going down the column, the atoms must be getting bigger, right? We can just even see that looking at the lithium and the sodium. Like, obviously, the sodium is bigger. Um, Not only is there more stuff, but like there's more orbitals. And we were just talking about how the sodium's valence electron feels less of nuclear charge because it's further away. So, yeah, the atom must be bigger. Hopefully, that's feeling good. Nothing crazy there. But the tricky one is thinking about going across a row. Mm. So I think it's pretty easy to look at this and say, like, okay, the logic's the same, right? If I go from lithium to beryllium to boron, they must be getting bigger because I'm adding more stuff. But it isn't the stuff that we add that's making the atom bigger, right? It's not really the protons or the electrons themselves. Really, what kind of determines the size of the atom is the orbitals. It's the electron orbitals. Maybe you've kind of heard that fun fact before that if the atom was the size of a football field, then the nucleus would be the size of a quarter in the football field, which really kind of goes to show you just how big the orbitals are compared to the nucleus. And so the fact that lithium, beryllium, and boron here all have the exact same orbitals means that they're roughly going to be equivalent in size, despite boron having more stuff than lithium. But that's not the only factor we need to consider. So I want you to use what I just said and maybe think for a second about how the trend might go and try and think about why the effective nuclear charge might change the size of the atom. Okay, so the reason why is that um, effective nuclear charge, right? It's basically the amount of proton force that each one of the electrons is feeling. So if it's going up as we move to the right on the table, that means those atoms are going to get smaller too because they're feeling more of a pull. They're feeling a greater force from the protons. So boron's actually quite a bit smaller than lithium. And if we look, that means that kind of in the second row of the periodic table, neon is going to be the smallest element and is in fact going to be smaller than lithium, despite having a lot more stuff. So kind of surprising, but that's how it works out. Okay, so the size decreases from left to right. So it's kind of the exact opposite of the effective nuclear charge. Now let's wrap up this video with the last periodic trends. So we covered the two really big ones and important ones. I've already kind of drawn them out here, but we've got I have two more written, and then we'll do a third one after that, and then we'll be done. So there's really five periodic trends. Um, and these next two are kind of a pair. They're really two sides of the same coin. So we've got ionization energy and electron affinity. So ionization energy is the energy needed to steal or take an electron from an atom. And electron affinity is the opposite. It's the energy that you get from giving an atom an electron. So when an atom gains an electron. So ionization energy, let's kind of think about this. I think the best way to think about this is to kind of zoom in to two extremes. So let's compare lithium again and fluorine. So let's compare lithium and fluorine. So if we scroll back up to lithium, right? So lithium has our valence electron, and if we're doing ionization energy, that means we're going to be taking it away. We're going to steal it. So if we take it away and steal it, um, what does that mean for the lithium? Let's kind of think about it from its perspective. Is it happier or sad to lose it? Um, And in this case, it's actually going to be pretty okay with it. It's going to be pretty happy about it because atoms, they more than anything want to have complete shells. They want to have complete shells. And another way of saying this is they want to have a noble gas configuration, right? So if lithium lost an electron, it would have the electron configuration of helium. And since the noble gases by default have complete electron shells, they're really unreactive, they're really inert, they're really happy to just exist the way they are. So lithium uh, is really happy to lose one electron, whereas fluorine, on the other hand, you can see that in order for it to get a noble gas configuration, in order for it to change into like neon, it needs to gain an electron. So it's going to take a ton of energy to steal an electron from fluorine, whereas lithium doesn't mind at all. You might even get some energy from it. Fluorine, it's going to take a lot of energy because it wants to gain an electron. It doesn't want to lose one. Okay, so kind of extrapolating that, ionization energy is then going to increase going to the right because it's going to take more work, more energy to steal an electron as you move to the right. And that also makes sense from our kind of effective nuclear charge standpoint, because as you're moving to the right, the effective nuclear charge is going up. So those electrons are more tightly bound in the atom, and therefore it's going to take more energy to steal them. And so, in fact, the ionization energy trend is going to match the effective nuclear charge trend exactly for pretty much the same reasons. Like I said, effective nuclear charge is kind of the origin of all the other ones. So it's also going to increase as we go up as effective nuclear charge increases. So yeah, I'll go ahead and draw that as a nice diagonal too. And then electron affinity, um, kind of the reverse, right? So energy gained from gaining an electron. So it's how much are we getting from gaining? Well, again, fluorine really wants to gain an electron. It's really excited to gain an electron. So you're going to get a lot of energy. So it's going to have the exact same trend as ionization energy. So I think that's kind of convenient. It's kind of makes it easier to remember, in my opinion. Um, and then one more periodic trend I want to talk about. This isn't one that usually you spend too much time with in Gen Chem, but as it turns out, I would actually argue it's the most important, and it's called electronegativity. And I'm sure you've heard that word before because in OChem, this is one of those things that comes up over and over again. And electronegativity is really basically just effective nuclear charge, but like a different word. I don't really want to go into the details of how they are different exactly because it's kind of overly technical, but it's suffice to say they're basically the exact same thing. So everything we've kind of thought about with effective nuclear charge really just applies to electronegativity too. But just kind of know that actually moving forward, electronegativity is way more common of a term. Like effective nuclear charge, I almost never see that in the MCAT, and you hardly ever see it outside of Gen Chem. But electronegativity as a term is something you'll see all the time, and I'm going to talk about it all the time. So that's why I really want to spend a lot of time today on the periodic trends. Yeah, if you're curious how they are slightly different, definitely look that up. It is kind of interesting, but really, I promise it's basically the same idea. So I'm kind of just going to say goodbye Z effective, goodbye effective nuclear charge. The king is effective or is electronegativity. So we're going to just replace it. It's the same trend. Okay. So all that being said, I think this is a good point to stop for the periodic trends. I hope this is really built on your physical intuition and things are making a little more sense. I hope you don't feel like you just have to memorize these now. And I'll see you in the next video.